The mathematical formula for calculating this effective nuclear charge is very simple. It's Z star is equal to Z minus S, where Z star is the effective nuclear charge, Z is the number of protons, or the actual nuclear charge, or the atomic number. All are the same. And S is the shielding constant. Now you're going to learn how to estimate the shielding constant using Slater's rules, and they're presented on the next 2 slides. Now that we're getting ready to calculate the effective nuclear charge, let's take and learn about Slater's rules and how it can be used to estimate the shielding constant S. First, we must write the electron configuration and group the electrons in the following way. The 1s electrons must be grouped by themselves. The 2s and 2p can be grouped together. The 3s and 3p are grouped together. The 3d is grouped by itself. The 4s and 4p are grouped together. The 4d is grouped together. The 4d is grouped by itself, and the 4f is also grouped by itself. So the bottom line is that the s and p electrons, with the exception of the 1s, will always be grouped together. Rule number 2 states electrons in higher groups, that's to the right in the list above, do not shield those in lower groups. So for example, if we're interested in an electron in the 3d orbitals, any electrons in the 4s, 4p, 4d, 4f will not shield the 3d electrons. Now, when we calculate the effective nuclear charge, we do it on a single electron. For example, what if your electron is either in the s or p orbitals? For example, say it was a 4p electron you were looking at. For ns or np electrons, electrons in the same ns or np group as the electron of interest contributes 0.35 to the shielding, except for the 1s, where 0.3 is more appropriate. B. Electrons in the n-1 grouping contribute 0.85 to the shielding. So if we're looking at 4p, that means the 3s, 3p, and 3d electrons each contribute 0.85 to the overall shielding. And C, electrons in the n-2 grouping and lower groups contribute 1 to the shielding. So all the electrons, 1s and the 2s and 2p, will contribute 1.00 to the shielding if you're interested in a 4p electron. If you want to calculate the shielding constant for an electron in d or f orbitals, electrons in the same Nd or Nf group as the electron of interest contributes 0.35 to the shielding. All groups to the left of the D or F electron of interest contributes 1.00 to the shielding. So you use Rule 3 if your electron is in the S or P orbitals. You use Rule 4 if your electron is in the D or F orbitals. So the answer to example 5, when we're looking at calculating the effective nuclear charge for a 4s electron in potassium, starts with writing the electron configuration and grouping the different orbitals appropriately. So that's what I did first. 1s2 is in a group by itself, 2s2, 2p6 are grouped together, 3s2, 3p6 are grouped together, and the 4s1 is grouped by itself. Now, according to the question, the 4s1 is the electron of interest, so we exclude that from our calculation. There's 8 electrons in the 3s and 3p orbitals. Since they're in n-1 orbitals, they each contribute 0.85 to the shielding. So 8 times 0.85 is the contribution by the 3s and 3p electrons. The 1s, the 2s, and 2p all contribute 1 each for each electron to the shielding. So for the 8 electrons in the 2s and 2p, they each contribute 1 to the shielding, and the 2 1s electrons each contribute 1 to the shielding. If you multiply these and add their results together, the shielding should be 16.8. To calculate the effective nuclear charge, you take the atomic number for potassium, 19, minus the shielding constant, 16.8, and you get an effective nuclear charge for potassium of 2.2. Let's try this with another example where we're looking at the d electrons instead of an s or p electron. We want to calculate the effective nuclear charge for a 3d electron in vanadium. So the solution to this question we have to start out the same way, by writing the electron configuration for vanadium and grouping the orbitals appropriately. 1s2, then in the second group is the 2s2, 2p6, and the third group is the 3s2 and the 3p6. In the fourth grouping, though, is only the 3d3, and in the fifth group is the 4s2. Now, since we're interested in looking at a 3d electron, we ignore the contribution, we ignore the 4s2 electrons because they do not contribute to the shielding constant. Since one of the 3d electrons is the electron of interest, the other two shield it somewhat. So each of the d electrons that are not accounted for, or that are not of interest to us, contribute 0.35 to the shielding. For the 3s2 and 3p6, the 2s2 and 2p6 and 1s2, all those electrons contribute 1 to the shielding according to Rule 4, because we're looking at a 3d electron. If you multiply the four values given below and then add them together, the shielding constant for a 3d electron in vanadium is 18.7. Calculating the effective nuclear charge requires us to subtract the shielding constant, 18.7, from the atomic number, 23. And that gives us an effective nuclear charge of 4.3. Now, I ask you at home to calculate the effective nuclear charge for a 4s electron in vanadium. And I want you to take and compare your answer to that for a 3d electron that you calculated for in example 6. Which electron do you believe should be lost first when vanadium forms V+? Calculate your answer and send it to me.